Welcome to Chapter 3 of our Precal book. In Chapter 3, we're going to be talking about two different but related types of functions. In these first two videos, we're going to talk about exponential functions, and the next two we'll talk about something called logarithmic functions. First, an exponential function, the basic form of that, your standard form, looks like this. Y equals a times b to the x power. It's called an exponential function because our variable is up in the exponent. The a is going to be some constant in this equation. It stands for the initial value that you have. And we'll see some applications later where that comes into play. This b can stand for one of two things. It can be a growth factor or a decay factor. There are exponential growth functions and exponential decay functions. We'll look at each here in a second. You can tell whether this is growth or decay based on the value of b. If your b value is larger than 1, you'll have exponential growth. If your b value is smaller than 1, you'll have exponential decay. So our first example here will be an exponential growth because it is 2 raised to the x power. We've left a is 1 here. It's like 1 times 2 to the x. So our initial value is 1. I want to explore what the graph of this looks like and also talk about the basic properties, the features, the domain and range, if they're asymptotes, things like that, if the function is not continuous somewhere. So I figured the best way to start this out, since our first one, is to use a table of values. And we can quickly do these in our heads or in our calculator, or even create a table in the calculator if you need to. If x is 0, 2 to the 0 power is 1. 2 to the first power is 2, 2 to the second power is 4, 2 cubed, 2 to the fourth. So what you notice about the y values, and this is why it's called exponential growth, our values are getting larger. As x gets larger, y also gets larger. Y is doubling every time, and that's because that growth factor is a 2. So in general, I kind of want to talk about in behavior of these graphs as well. As x approaches infinity, then the y value is also going to approach infinity. The bigger you make x, the bigger you make y. And we start to see some of these points on our graph. We have 0, 1, so our y-intercept is going to be 1. 1, 2, 2, 4. We see not only does this function increase, but it increases very quickly. Every time we increase the x value by 1, we're doubling the y value. So you can see, all the way, once I get to x equals 4, I've already got values way up here on my graph. Exponential functions grow more quickly than any kind of polynomial function. They'll grow faster than linear functions, quadratic functions, cubic functions, even x to the 100th power. Eventually, an exponential function will grow more quickly and approach infinity more quickly than any other type of function. So if we look at half of our graph, it sort of looks like half of a parabola. Oh, that's a terrible graph, as usual. Kind of looks like half of a parabola there, but it is much steeper than a parabola. The rate of change, the average rate of change, the average slope is much larger than it would be in a quadratic, especially as you get x to be values that are larger. Now what if x is a negative value? If I have 2 to the negative first, 2 to the negative second. The key here to remember is that if you have a negative exponent, it takes your expression and it moves it to the denominator. So 2 to the negative 1 power is 1 over 2 to the first. 2 to the negative 2 is 1 over 2 squared. 1 over 2 cubed, and so on. So these values that we're getting out are fractions. When x equals negative 1, our y value is a half. This is a fourth, and an eighth, and a 16th. So as x gets more negative, we get these fractional values. So what do you think? The more negative we make x, what kind of values do you think y is approaching here? If I put in like negative 100 for x or something. My guess is if you try to do 2 to the negative 100th power in your calculator, it's so small your calculator will just pretend that it's actually 0. It's not quite 0, but it is approaching 0. As x approaches negative infinity, our y values approach 0. So, since we have a value that y is approaching as x approaches positive or negative infinity, this means we have a horizontal asymptote happening. The x-axis, y equals 0, is our horizontal asymptote there. Our domain, we can use any value we want in an exponential function. Our domain will be all real numbers. So you can say negative infinity to infinity. You can write out all real numbers. You can use that kind of R symbol for those. Your range, notice we're only getting positive values out here. Even with negative x values, we're getting slightly positive fractions here. So our range is just going to be y values that are greater than 0. So going from 0 to infinity. Right. That's an exponential growth function. This is growth. You can tell that from the graph. As x gets larger, y gets larger, our y values are growing. Right? Once again, with our graphing, if you know your transformations, things are a lot easier. We can graph y equals 2 to the x power plus 4 using transformations. We know exactly what 2 to the x looks like from the last board. That plus 4 is going to move our graph up. So you can take that same graph, which was kind of here. It had a y-intercept of 1, you'll recall, so kind of dot this in a little bit. Looks kind of like that. Everything on that graph will move up 4 units, including that horizontal asymptote. So that y equals 0 asymptote will move up 4, and our new horizontal asymptote will be at y equals 4. So instead of here is my guideline, here will be my guideline. My y-intercept, instead of being at 1 like it was initially, will move up 4 units and be at 5. You can double check that by plugging in 0 for x. 2 to the 0 power is 1 plus 4. Your y-intercept's 5. The shape is the same. Use that y equals 4 as your guideline, as your asymptote. Right? If that minus 3, like on the pink one here, if we've got 2 to the x minus 3 power, that minus 3 is now inside of our function. So that means it's going to move our graph to the right 3 units. Right? So this will go right 3. So that original graph, which looked kind of like this, everything will shift to the right. It's not going to change your horizontal asymptote now because we're taking y equals 0, moving it to the right 3, it's still the exact same line. So this whole thing just shifts over. It's like, for example, this place where y equals 1, instead of being when x is 0, instead of being the y-intercept, it's going to move to the right 3 units. So that point's going to be here instead. That point that was at 1, 2 before will move to the right 3 units, and so on. That asymptote stays the same. Graph looks kind of like that. Didn't talk about domain and range in either one of these yet. Your domain for any exponential function is all real numbers. All real numbers. All real numbers. Negative infinity to infinity for any exponential function. Your range, that's your y value, so if you're moving the graph up or down, you're going to affect your range as well. So your range here has moved up 4. We can only go the open interval from 4 to infinity. The range on this one did not change. We slid to the right. Our y value stayed the same. We go from 0 to infinity still, just the positive y values. Horizontal asymptote can move. Remember, your range and your horizontal asymptote are going to be connected because they're both related to the y values. So y equals 4 here, still y equals 0 in this case. So you can use your transformations to help you. So we've talked about exponential growth and graphs of exponential growth and their transformations. What now if we have exponential decay? Right? This is going to be exponential decay. I know that because this b value is a half. It's less than 1. So we're going to be graphing an exponential decay function here. Decay has a c in it now. There you go. So exponential decay, again, let's kind of explore this with a table of values. Well, anything raised to the 0 power is going to be 1. So notice our y-intercept here is the same as it was for the 2 to the x power, for the exponential growth. And that's going to be true of any exponential function before we do transformations. If it's just something to the x power, well, anytime I plug in 0 for x there, my output will be 1. So the y-intercept would always be 1. 1/2 to the first power, 1/2 squared, square the top, square the bottom, 1/2 cubed, 1/2 to the fourth. So now what's happening is x is getting bigger. If I start to plot these values, as x is getting larger, y is getting smaller, and specifically, y is heading toward the value of 0. So we've got a horizontal asymptote again at y equals 0, based on this fact here. Remember, horizontal asymptotes happen as x approaches positive infinity or as x approaches negative infinity. So what happens with negative values for x? Well, if I'm doing 1/2 to the -1 power, remember negative exponents move things to denominators, but if they're already in denominators, they move them back up to the numerator. So 1/2 to the -1 power is 2. 1/2 to the -2 power, well, it's like bringing the 2 back up to the numerator to the second power, so 4. 1/2 to the -3, flip it, 2 cubed, 2 to the fourth. So now as x gets more negative, the y values are getting larger. -1, 2, -2, 4, -3, 8, -4, 16 will be all the way up here. So do you notice that all the y values are the same as they were for the exponential growth, for the 2 to the x? They're just sorted differently. They're just paired up differently with the x values. These are the same y coordinates, but on opposite sides of your graph. Now your function is decreasing, and that's why it's exponential decay. That should approach the y-axis, or the x-axis there. That should hit that point there, and that point there, and that point there. All the same y values, but in different places. Notice this is the same graph as 2 to the x power, only it's flipped. It's reflected across the y-axis. And if you remember what reflects a graph across the y-axis in your transformations, it's having a negative in your equation. It's like having 2 to the x, only that x is negative. So 2 to the -x is the same as 1/2 to the x. So if you see a b value greater than 1 with a negative exponent, that's still exponential decay. So it's the same as having like a half there. Domain and range here. Domain's all real numbers again. Range is just your positive values for y, 0 to infinity. Okay? So that's how to graph exponential decay functions. And we could do transformations just the same way with these if we wanted to. Now, I want to talk about applications. What are we actually going to use some of these exponential functions for? Rewrote our basic growth decay function here. So our application here says, I'm going to grab my calculator while I'm reading this. It says a colony of bacteria is growing at a rate of it's growing at a rate of 20% per hour. And I have 500 bacteria in the colony now, and I want to know how many there are going to be 2 hours from now. All right, well now, oh, you can't see me yet. Now, that A value comes into play. That A stands for your initial value. So we have 500 bacteria at the beginning of this problem. So if we're looking for what the output's going to be, we're starting with 500 bacteria, and then we're multiplying by B, which is our growth factor. To figure out that growth factor, we take our 20% here, change that 20% to a decimal, so move that 2 places to the left. So 0.20 or 0.2 is fine. If you want it to be growth, we want this to be greater than 1, so you're going to add that decimal to 1. So you're going to add that to 1. So 1.20 or 1.2 is going to be our growth factor there. indicating 20% growth. And then after 2 hours, that 2 hours is your input. So square that. That's how your growth model is going to look. I'm going to type that into my calculator here. 500 times 1.2 squared. And I get 720 bacteria after 2 hours. All right? Well, what if I wanted to extend this time period? What if I wanted to go 6 hours? It's the same initial value, and it's the same growth factor. It's a constant rate of 20% growth per hour. So this growth factor remains 1.2. We just change our x value to the 6th power. So I'm going to put that in my calculator. By the way, cool thing in your calculator, if you don't know this, if you press second and enter, it brings back the last thing you typed in. So instead of typing the whole equation again, you can hit second enter and then just go change your exponent to a 6. Well, now I get 1492.992, which has, we're talking about a number of bacteria. I guess we probably really want a whole number there. So you could round that up if you wanted to 1493. Or you could say, well, that's really just 1492 because that last bacteria never totally formed, although it was super close there. Either one of those is going to be acceptable. Okay. And then finally, I'm just going to show you this to kind of illustrate what exponential functions do again. What if we do this after 2 days? What if I take my 500 growing at 20% per hour, and now 2 days, so 48 hours pass? Check out what happens when you put that in the calculator. I get a giant number. I've got, if I did this correctly, I've got 3, 1, 5, 9, 8, 7, 4. I'll just round it to the whole number. Look, that's 3 million bacteria in 2 days' time. You start with 500 bacteria, and this 20% growth rate is not out of the question in a lab setting if you're actually trying to grow the culture. After 2 days, you know there were 3 million bacteria, mathematically speaking. Now, tomorrow we might talk about, and think about this. In real life, why might we not really end up with 3 million bacteria after those 2 days? Mathematically, it's true. And this is the key about exponential growth functions. They grow very rapidly. I told you they grow faster than polynomial functions, lines, parabolas, anything else. You see that happening here. After 2 days' time, 500 bacteria can turn into 3 million bacteria. So, but let's talk tomorrow about why that might not happen in real life. So I'm looking for scientific answers. So you science people out there, be thinking about some things that we can discuss there. All right. The final application I want to talk about today, and the bell's going to ring in like 5 minutes, so we'll see if we get this done before the bell rings. The most common place that you'll see exponential functions in your everyday life is getting interest at the bank. You know, if you were in middle school, you might have talked about simple interest, but really simple interest isn't what happens in real life. You get something called compound interest, and the difference is in compound interest, you get interest on top of your interest every interest period. In simple interest, you're always going back to the amount you invested initially. So I'm going to kind of get out of the way here for a second, make sure you can see all that, and make sure it's framed okay in the video. All right. So here's our compound interest formula. A just for the amount that you have at the end, right? And to get the amount at the end, we start with our principals. We call this in finance. That's simply the amount that you invest. Notice it's like the initial value in the problem. Then we've got 1 plus R, which stands for your interest rate, as a decimal. So we're going to percent interest rate. We'll change that to a decimal. N is the number of interest periods per year. Different banks will do different things. Some will give you interest once a month. Some will give you interest only once every 3 months, once a day even. So N is how many interest periods you get every year. And then T is the time in years. So I'm going to do an example here with you. Let's say we're investing $1,000, and we'll say it's a 1.3% interest rate. You might see APR in advertisements. That's annual percentage rate, just the rate you get at over the year. And let's say we're going to compound this monthly. For let's say 5 years. So $1,000 is my principal. So the amount I'm going to get at the end is $1,000. 1 plus this 1.3% I need to change to a decimal. 2 places to the left, so that's 0.013. N is the number of interest periods every year. If my interest is being compounded monthly, then I'm getting interest 12 times every year. That N value is 12. Notice that's that same N value up here. And then the time in years for 5 years. So I'm going to take my $1,000. I'm going to invest it for 5 years. I'm not going to touch it at all because I'm trying to get my money to grow. When I put that in my calculator, it's not great news. I make $67 and change in 5 years' time. And that's because that's a pretty low interest rate. It's a low interest rate, but it's a realistic interest rate if you're putting something into a savings account or something. So we've got time. We'll talk about investments and maybe some ways to make money at a little better rate, a lot better rate than this, because we don't want to be putting $1,000 in the bank and only making 67 bucks after 5 years, right? So that's compound interest. And finally, now the bell's going to ring. Why do they? I'm up here on a day off of school. Why are the bells ringing? What? That doesn't make sense to me. Anyway, some banks, instead of giving you interest once a month, once a day, once a quarter, they will give you interest all the time. They will do what they call continuously compounded interest. This sounds like a great deal. Just, hey, we're just giving you interest all the time. Come invest in my bank. Now, this P is the same principal, and this R is the rate, and this T is the time. This E is actually a number. This E is not a variable. This E is a number in your calculator. You'll find it, see? You'll find the E in your calculator up above the LN button, where it's a lowercase e. We'll talk about where that E comes from a little bit, but it's approximately equal to 2.718. I'm just kind of telling you that for reference. Don't type in 2.718 because that's rounded. Use your E button. But that E button is there for continuously compounded interest. So let's do the same example. Let's say $1,000, 1.3%, 5 years, but now it's going to be continuously compounded. And I want to know how much I'm going to have after those 5 years. My amount's going to be 1,000 times that E. Still change this R to a decimal, so 0.013 for 5 years. And then we'll see what that does. What you'll find is that what sounds like a great deal, that continuously compounded interest, really doesn't have a big impact on the amount of money that we make. In fact, I'm rounding up and I've got an extra 4 cents, it looks like. I'm getting $1,067.16 instead of the 12 cents I got compounded monthly. So not a big impact for continuously compounded interest, but banks will often do this to simplify the process of calculating interest using that E value in there, right? So that's an introduction to exponential functions and their applications. Tomorrow in class, we'll start working some of these problems, and we'll talk about why we can't get 3 million bacteria in 2 days.